at the syllabus, it appears I somehow got a day behind. And then I also just looked on Moodle and realized that because I didn't realize a day behind, I didn't put the stuff that I needed to put on Moodle. So today we are going to cover multi-frequency power analysis, as well as effective values. And effective values leads us into complex power. So on Thursday, I'm going to cover complex power and power factor correction, if at all possible. Both of those topics should be a review of Circuits 1 material, so I feel justified that I can squeeze everything in one go and get us back on track. All right, so let's start talking about multi-frequency power. And to make this relatively brief, we're going to what would be considered, from a circuit analysis standpoint, an incredibly simple circuit, but we're going to be able to get all the information that we would want out of it to get what I want. So let's see. Frequency. My pen thing will work. Excuse me. So let's consider this trivial circuit. We have a current source. Let's call this guy IS1 of T. Don't know why my pen is misbehaving this morning. Let's actually make this ever so slightly harder. Call this guy IS2 of T. This will be a 5 ohm resistor. This will be a 2 Henry inductor. We're trying to find this voltage. Let's call this guy V of T. And we're going to be trying to find the power supplied by our current source IS1. So let's say that IS1 of T is 3 cosine 2t, and IS2 of T is equal to 2 cosine 3t, and both of these are in amps. So this is a multi-frequency circuit, and we need to know that voltage drop over that middle branch, okay? So how could we go about figuring that out? Let's start there.
Superposition?
Right, it's literally the only way that we can do it is superposition. So so with IS1 on and IS2 off, we can see pretty much by inspection that our voltage V phasor is going to be the phasor representation of our current IS1. What's that going to be?
3 angle 0.
Multiplied by the impedance of our branch in the middle there, which is going to be what?
5 plus 4j.
5 plus J4. All right. So 3 times 5 plus J4 gives me 19.209 angle. Oh, I'm in radians. Hold on, mode. $38.660. Let's call that prime so that V prime of t is then 19.209 cosine 2t plus 38.660 degrees volts. And we can easily see that with IS1 off and IS2 on, V double prime should be the phasor representation of IS2, which is going to be 2 angle 0, multiplied by the impedance of that middle branch, which is going to be 5 plus J6. $15.620 angle 50.194 degrees. So the double prime of t is then 15.620 cosine 2t plus 50.194 degrees amps, and thus V of t is equal to 19.209 cosine 2t plus 38.660 degrees plus, sorry, this shouldn't be amps, this should be volts because we're looking at a voltage, 15.620 cosine 2t plus 50.194 degrees volts.
Shouldn't that second one be 3T?
You're absolutely right. Otherwise, we could add them together. What I'm trying to do now is define a current through this branch as well, but my stupid fat fingers are getting in the way. We could say that the current through that branch, I of t, we could just do KCL at the top node and find that I of t is going to be IS1 of t plus IS2 of t. Don't need to do any circuit analysis. That's why I made this one so simple. So that's going to be 3 cosine 2t plus 2 cosine 3t. So if we wanted to get the power absorbed by that middle branch, let's call it P mid as a function of time, it would simply be V of t multiplied by I of t. Nothing crazy there. The issue that we're going to have is that we're going to have a lot of different cross-multiplied terms. So let me try to write this out a little bit better. So we're going to have 19.209 cosine 2t plus 38.660 degrees plus 15.620 cosine 3t plus 50.194 degrees Both of these are voltages multiplied by our currents. 3 cosine 2t plus 2 cosine of 3t. So we're going to have to FOIL this multiplication of trig functions out. And it's going to get a bit tedious. So what we're going to have to do is kind of break it down into digestible bits. So let's take a look at things first. So we're going to have 19.209 cosine 2t plus 38.660 degrees volts multiplied by 3 cosine 2t plus 19.209 cosine 2t plus 38.660 degrees volts multiplied by 2 cosine 3t amps. Let me put my unit over here. Come on, pen thing. Plus 15.620 cosine 3t plus 50.194 degrees volts multiplied by 3 cosine 2t amps plus 15.620 cosine 3t plus 50.194 degrees volts times 2 cosine 3t amps. So this is all our different little cross multiplication pieces. What we're going to do is we're going to be applying this trig identity that says cosine of theta 1 multiplied by cosine of theta 2 is equal to 1/2 cosine theta 1 minus theta 2 plus 1/2 cosine theta 1 plus theta 2. We're going to see some interesting things pop out of this, okay? So if we look at our first multiplication term, that's going to give us, and we have, we're also multiplying by a factor of 19.209 volts and a factor of 3 amps. So that's going to give us 1/2 times 19.209 volts times 3 amps times cosine of, so 2t plus 38.660 degrees minus 2t is just cosine of 38.660 degrees plus cosine of 2t plus 38.660 degrees plus 2t gives us 4t plus 38.660 degrees. So is everybody okay with that first bit of multiplication that I'm doing by applying the trig identity I've put in orange?
That's good.
All right, I want you guys to notice something right off the bat here. Our circuit contained 2 frequencies, 2 radians per second and 3 radians per second, and so far, based on 1/4 of our calculations, our power already has two frequencies, 0 radians per second and 4 radians per second. So our power is going to have some weird looking terms that aren't going to match the frequencies that we would necessarily expect them to match based on the excitation frequencies of our circuit. So if we keep this ball rolling, we're going to have a 1/2 19.209 volts times 3 amps. So now I'm going to have cosine of 2t plus 38.660 minus 3t. So that's going to look like a cosine of negative t plus 38.660 degrees plus cosine of, let's see, now I'm going to have to add the things together. So 2t plus 3t is going to give me 5t plus 38.660 degrees. So now we have a negative frequency. Now that may seem a little bit odd, but hopefully you guys can recall that cosine of negative x is equal to cosine of x. And so I can actually transform that to a positive frequency pretty easily. I just need to factor out a factor of -1. So that would be cosine of positive t minus 38.660 degrees. All right, for our third term, how much room do I have? I'm going to have 15.620 volts times 3 amps cosine, let's see, so this is 3t minus 2t is positive t plus 50.194 degrees plus cosine, let's see, 3t plus 2t is 5t plus 50.194 degrees. And lastly, I'm going to have 2 amps, let's see, cosine. So 3t minus 3t is going to give me 0, so that's just 50.194 degrees plus cosine of 6t plus 50.194 degrees. All right, so let's look at this thing. We have a DC term, a 4 radian per second term, a 1 radian per second term, a 5 radian per second term, another 1 radian per second term, another 5 radian per second term, a DC term, and a 6 radian per second term. So unless I am mistaken, we have, let's see, I think it's 5 distinct frequencies, DC terms, and then 1 radian per second, 4 radian per second, 5 radian per second, and 6 radian per second. Yeah. So 5 different frequencies are being have a power component, even though we're exciting only at 2 frequencies. So we will need to combine our DC terms. So that's going to be where we have 1/2 times 19.209 times 3 times the cosine of 38.66 plus 0.5 times 15.620 times 2 amps times cosine of 50.194. So our DC term looks like 32.499, let's just call it 32.5. Our next lowest frequency term is going to be are 1 radian per second, guys. So what I'm going to have to do to add these together is effectively convert them into complex numbers and then add them together and go back. So that is going to be 1/2 times 19.209 times 3 amps with an angle of negative 38.660 degrees. And to that, I'm going to add 1/2 times 15.620 times 3 with an angle of 50.194 degrees. And that gives me 37.5 cosine t. So those degrees, yeah, they're almost, I'm actually getting an angle of minus 0.0006, but that's so small I'm not going to bother counting it there. I'm just trying to make sure that I punched in all my numbers right, because that seems potentially odd, but you know, it is what it is.
Dr. Hartman, I
Yeah.
believe the 3 amp multiplied thing on the first cosine t term should be 2 amps, right?
You're correct. Thank you. So let's, all right, so that should definitely change some things. Thank you very much. All right, good. Now it's no longer giving me a phase angle of 0, which seemed very strange to me. 30.593 cosine t plus 11.309 degrees. All right, then we have, let's see, our cosine. So that took care of DC, single. So now we're going to have 4, 5, and 6. So our 4 term is going to be 0.5 times 19.209 times 3. 28.814 cosine 4t plus 38.660 degrees. Now we're going to have our 5t terms, so this guy and this guy. So 19.209 times 2 with an angle of positive 38.660 plus 1/2 15.620 3 with an angle of 50.194. $42.425 cosine 5t plus 44 point, let's just call it 45 degrees. And lastly, I'm going to have 0.5 times 15.620 times 2. Oh, well, that should have been easy enough. 15.620 cosine 6t plus 50.194 degrees watts. So, in a multi-frequency circuit, hopefully you guys have observed just how ludicrously tedious this can be to calculate the instantaneous power. Instantaneous power in general is probably a little bit more than most electrical engineers need. And in a multi-frequency circuit, it gets bad real quick. So let me ask you guys, hopefully, what will be a pretty simple question. What is the average power absorbed by that branch?
The DC component.
Yeah, the DC component, 32.5 watts, right? So this guy right here is P average. Now what's very interesting, or at least it's interesting to me, if I could get my stupid pen thing to write the letter G, there we go, is that P average can be determined effectively by doing superposition. And so what I mean by that is I think we might need a factor of 1/2 here. Yeah, we'll definitely need a factor of 1/2 because we're multiplying sinusoids. Okay, so what I mean is a short-term way of finding P average would be 1/2 Vm prime Im prime plus 1/2 Vm double prime Im double prime. So if we did the math here, this would be 1/2 times our 19.209 volts times 3 amps plus 1/2 times 15.620 volts, 2 amps. Let's double check my math here. I'm getting something wildly different. Why am I getting something not correct? So when IS1 is on, well, okay, so I think I needed to multiply by cosine of, all right, so. This is what happens when I don't prepare. So let's try this again. 1/2 times 19.209 times 3 cosine of 38.660 plus 1/2 15.62 times 2 times cosine of 50.194. There we go. And this will give us 32.499 or 32.5 watts. All right, so the reason why that's interesting to me is because power is inherently a nonlinear term because it depends on either the square of the voltage or the square of the current, at least in a DC circuit. It definitely depends on the product of the two waveforms, which is inherently nonlinear. But the average power works because if we were to integrate this big ugly thing that we have here, over exactly one period, and we could figure out what the periodicity of this guy is, because we would just have to look for the lowest common integer multiple of the frequencies to figure things out here. So the periodicity would be based on a frequency of probably 30 radians per second or something like that. So we'd have to look at some number of cycles of 30 radians per second to be able to get everything together. But if we took the integral of this guy over an integer number of periods, we would find that all of the terms that have a cosine blah, blah, blah part with them wind up going away because the average value of a cosine function is exactly 0. So that's why we're left with just this DC term, and this guy down here gives us a shorthand way to get that result without having to fumble our way through so many steps and cross multiplications. And, you know, even I made errors in bookkeeping and putting things in the wrong place. So this bottom equation is a much, much more straightforward way to find the average power in a multi-frequency circuit. And 9 times out of 10, we're going to be significantly more concerned with the average power than the instantaneous power anyway. Because when we design circuits and things like that in the real world, we're never really looking at, like we look at the maximum values of voltage and current and things like that, and usually current, to get a sense of what size of a breaker we might need to prevent damage to things. But as far as the actual operation of the circuit, everything is based off its average value. Okay, so I think I gave you maybe some homework problem to suffer through this kind of thing. Shouldn't be too crazy difficult. It's just applying these two trig identities. All right, let's move forward to effective values, something that's going to be hopefully a lot less insane. So this should largely be a review, but let's talk about things just a little bit. So what I am trying to draw here is a standard receptacle that's used in the United States. Who among you can tell me what voltage this guy is supposed to have? Like if you go try to plug something up in your room, what's the assumed voltage out of your receptacle?
It's 120 volts, right?
120, okay? So that 120 comes from our hot wire, which I'm drawing in red here. And then I'm going to draw in gray our neutral wire. And then this guy here at the bottom is typically green, and it's our ground wire. And in circuits involving a receptacle like this, the ground isn't really part of the circuit. So the neutral is effectively playing the role of ground, and you will often see that the neutral wire and the ground wire are tied together or bonded together outside of your home, literally through a grounding rod, which is a piece of metal that's stuck into the earth so that there is a reference potential for your system. All right, so you're saying that there is 120 volts between these two terminals. Positive polarity on the hot side, negative polarity or the reference is on the neutral side. So my question to you is, do our outlets provide DC voltage?
I don't think so, no.
They do not. They absolutely provide a steady state sinusoidal voltage. The steady state sinusoidal voltage that is supplied by an outlet, so let's call this V receptacle. If my stupid thing, as a function of time, is 169.706 cosine. Because we're in the United States, we're operating at a linear frequency of 60 hertz, which means we have an angular frequency of 120 pi hertz, plus whatever phase angle we happen to start observing our signal at volts. So the question that we're going to address today is, how in the heck does this 169.706 keep getting called the 120 that we are familiar with? And the answer is that the 120 volts is the effective value of that sinusoidal voltage. So an effective value is really just an engineer's shorthand notation for saying this time-varying signal is going to supply just as much power as a DC signal. So we know that for a DC signal, P average is simply VDC squared over R, or equivalently IDC squared times R, right? For a DC circuit, those are our relationships. For, excuse me, an AC circuit, we know that the average power absorbed by an arbitrary resistor should be, let's see, it's going to be the integral over one period, so let's call this from 0 to t, of the instantaneous voltage waveform squared divided by the resistor value integrated with respect to time, or similarly, it could be the integral over one period of the instantaneous current waveform multiplied by R with respect to time. Where we know that P is equal to I times R, and we're also using Ohm's law to express in the first case I as V over R, and in the second case V as I times R. So we're just using simple Ohm's law and power relationships, and the definition of, sorry, I need to divide each of these by one period. The average value of a function, right? So the average value of a function is you take the integral over one period and then divide by the length of the period, and that gives you the average. Well, we can equate our relationships. So I could say that VDC squared over R is equal to 1 over t integral from 0 to t of V squared over R dt. The reason I'm doing this is because they both represent the average power, And what I'm trying to do is I'm trying to find a DC value that gives us the same power as our waveform. We could divide both sides by a factor of 1 over r, and then take the square root, and that would give us VDC, which I'm going to start calling now V effective, is simply the square root of 1 over t times the integral over 1 period of the square of our voltage waveform. So the effective value is simply the DC value that supplies the exact same amount of power to an arbitrary resistor as that voltage waveform V of t. And I could do a similar derivation, but I'm just going to jump ahead, and we can see that I effective would just be 1 over t integral 0 to t of, I squared dt, like so. So we have a simple and easy mathematical formula to apply. These are valid for any and all periodic functions. So we're going to look at a couple. So let's say that I have, I'm just going to make one up here. A voltage waveform like this. It's simply a series of these pulses. Let's say that this has a value of 10 volts. This is at 1 second, 0, 1, 2, 3, 4, 5, etc. So this is time measured in seconds. Voltage is measured in volts. So we just have a periodic trail of these odd-shaped pulses. We can find the effective value of this pretty easily. So let's see how we go about doing that. Well, V effective is, by definition, the square root of 1 over t integral over 1 period v squared dt. So my question to you guys is, let's start with something easy. What is the period of the waveform that I've drawn?
3 seconds.
3 seconds, right? So we're going to have 1 over 3 seconds integral, and I'm going to split my integral up. And the reason I'm going to split my integral up is because I have effectively a piecewise function. So I have some certain thing from 0 to 1. So over the time interval from 0 to 1, how is my voltage waveform behaving?
It's not changing.
It's constant. Okay, so what's its value?
10 volts.
All right, so I'm going to put in 10 volts, and I need to remember to square it, and then I take the multiply by dt. Plus, let's look at it over the interval from 1 to 2 seconds. So it has a slope. What's its slope?
Slope will be negative 10t.
Negative 10. Come on, pen thingy. What I'm trying to do, I need negative 10 volts per second. All right, multiplied by our variable here. In this case, it's not just going to be t. And the reason it's not going to be t is because we've time shifted this thing by 1 unit to the right. So I'm going to call that t minus 1 second. And I'm going to have to add my intercept at t is equal to 1. So where does, like what value does the voltage have at exactly t is equal to 1? It's still 10 volts. I'm going to square this guy. So before I go forward here, do any of you guys remember anything at all about time shifting things from your pre-calculus class? Because the math that I just did right there makes perfect sense to me, but it may make absolute garbage sense to you, and that's we can't work like that. We need to be on the same page.
Are you basically saying that you shifted the whole graph to the left by 1 second?
Pretty much, yes. So that is exactly what I did. I put it in the y is equal to mx plus b format, where I considered my new horizontal axis to be at t is equal to 1. So that's where I got that intercept from. And me shifting the graph by 1 time unit to the right, or shifting the vertical axis by 1 time unit to the right means that I have to have a t minus 1 here. So this minus means I'm shifting to the right. If I had a plus sign, it would mean I was shifting to the left. Okay, I feel at least that Cord understands what I'm doing, so I'll take that as some sort of consolation. My last bit that I'm going to have here is the integral from, oh, and this is with respect to time, is the interval from 2 to 3. What's my voltage at over this interval?
0 volts.
0 volts. So square that dt. So I'm just trying to make it very, very obvious that I am actually integrating over the full 3-second period of this guy. All right, so this is going to give me square root of 1 over 3 seconds. All right, so the integral of 10 volts squared is going to be what?
100t.
So 100 volts squared t, and then we're going to evaluate it at 1 and 0, right? Nothing too wild there. This guy in the middle here is going to take a little bit of doing. So we have, I'm going to, so let's play around up here real quick. So I have negative 10 t minus 1 plus 10. So that's the same as negative 10t plus 10 is negative 10t plus 20. Everybody okay with that?
Looks good.
All right, so when I square that guy, I'm going to have, let's see, so this is going to be negative 10 volts per second t plus 20 volts times that same thing, negative 10 volts per second t plus 20 volts. So negative 10 volts per second times negative 10 volts per second is going to give me 100 volts squared per second squared. T times t gives me t squared. Negative 10 volts per second times 20 volts gives me minus 200 volts squared per second. P. I'm going to have another one of those, so let's just call it minus 400 to make things easier. And then I'm going to have 20 volts times 20 volts plus 400 volts squared. Okay, so that looks okay to me. So and this is going to be evaluated at 2 and 1. And then my last bit is obviously plus 0. All right, so now we're getting into just some straight math here, it looks like. So 1 over 3 seconds. So 100 volts squared times 1 second is 100 volts squared second minus 100 volts squared times 0 seconds is just going to be minus 0. So that takes care of that bit. Then we're going to have (100 volts squared per second squared multiplied by, let's see, 2 seconds squared. (1 second squared). So 400 volts squared per second times 2 seconds plus 400 volts squared per. Oh, I didn't integrate. That's why I was confused about the units. So what I mean is I took this guy right here and I just dropped it straight in, but I'm supposed to integrate that, right? So that would be this should be t cubed over 3. This should be t squared, so that's over 2, and this should be t. Okay, now things are, excuse me, a little less awkward because I was going to have units of volts squared times seconds on the first bit and volts squared on everything else. Okay, sorry about the math error. So let's get back to this guy. 100 over 3 units of volts squared per second squared times 8 seconds cubed minus 100 over 3 volts squared per second squared times 1 second cubed minus 200 volts squared per second times 4 seconds squared plus 200 volts squared per second times 1 second squared plus 400 volts squared times 2 seconds minus 1 second. Make things a little bit easier. All right, and now we should be in a place where we can just plug this in calculator. So I have 100 plus 100 over 3 times 8 minus 100 over 3 minus 200 times 4 plus 200 plus 400. 400 over 3 multiplied by a factor of 1/3. So what I have is the square root of 1 over 3 seconds times 400 over 3 volts squared seconds is going to give me the square root of 400 over 9 volts squared. (20 over 3) or 6.667. So this odd-looking waveform that we have up here supplies the exact same amount of power to an arbitrary resistance as a 6.667 volt DC source. Now I'm going to start using a particular unit to specify when I'm using an effective value, and that unit is volts RMS. The reason that I use the units volts RMS is because we are performing an RMS operation, meaning we are taking the square root of the arithmetic mean of the square of the voltage signal. And we could do a similar thing for, excuse me, a current waveform. So we have roughly 15 minutes left, so let's look at something pretty simple, in my opinion, in comparison. Let's say that we have I of t is equal to Im cosine omega t plus some phase angle theta I. And we want to figure out what the effective value for this guy is. Excuse me. So the first thing that we're going to need to know then is that our expression for I effective is square root 1 divided by t integral 1 over 1 period of I of t squared dt. So does anybody remember the relationship between omega and the period of a sinusoidal waveform?
The period equals 2 pi over omega.
Okay, so you're saying t is equal to 2 pi over omega. I actually agree with that, so I won't need to draw out our picture so we can figure things out. Great, thank you, Sadie. So from this, we can simply substitute things in. So 1 over t is going to look like omega over 2 pi integral from 0 to 2 pi over omega. So when we square our cosine function, we are going to have, we're going to use that trig identity again, cosine theta 1 times cosine theta 2 is equal to 1/2 cosine theta 1 minus theta 2 plus 1/2 cosine theta 1 plus theta 2. So that's going to give us 1/2 Im squared. And then we're going to have cosine theta 1, where theta 1 is omega t plus theta I minus theta 2, which is the same thing. So those guys are going to cancel each other out. Cosine of 0 is 1, so everything's hunky-dory there. Plus 1/2 Im squared cosine of twice omega t plus twice theta I dt. All right. So we can split this up into two integrals. Im squared cosine twice omega t plus twice theta I. So let's look at the second integral. So what we are doing there is we are integrating cosine of 2 omega t over exactly 2 periods, right? Because our period of 2 pi over omega is what we have when we have an angular frequency of omega. So if we have an angular frequency of twice omega, this period represents 2 periods for the double frequency term. Does that make sense?
Yes, sir.
So my question for you all is, what happens so let's see. When I integrate over 2 periods of a sinusoid, what do I get?
Cancels out, right?
Yeah, if we integrate over any integer multiple of periods, the answer is 0. So this integral is 0. So what do we got going on with our first integral? Well, that's a constant, right? So we are going to have 1/2 Im squared times omega over 2 pi times the integral from 2 pi over omega to 0 of dt. Well, that's simply 1/2 Im squared times omega over 2 pi multiplied by 2 pi over omega. These guys all cancel each other out. And what we're left with is Im divided by the square root of 2. So the effective value for our sinusoidal current in this case is simply the magnitude of the sinusoid divided by the square root of 2. Now, notice our current waveform had a specific frequency and a specific phase angle. And our effective value is independent of those. So we can say that any sinusoidal voltage or current, the effective value of that sinusoid is simply the magnitude divided by the square root of 2. So we have 5-ish minutes, so I'm going to introduce one very last extraordinarily simple concept, okay? And that is the Rms Phaser, because we're going to be using Rms Phasors a lot in the coming several classes. So if we have a time domain voltage, V of t, is equal to Vm cosine omega t plus theta v. This is time domain. We know that we can express it in the frequency domain as what?
VM angle theta v.
All right, perfectly correct. So call this quite often phasor domain, so I just want you to know I'm going to use those two terms interchangeably. All right, so the RMS phasor domain, I am going to denote by, instead of having a bar over it, I'm going to have a tilde over my signal. And this is simply going to be VM divided by square root of 2 with an angle of theta v, which is just V effective angle theta v. This is the nomenclature that we're going to use, or the domain that we are going to be in when we handle all of our complex power relationships, and from then on also when we're doing three-phase power and things like that. So I want to be very, very clear here that if I give you a phasor and it has units of volts or amps, they are a frequency domain phasor. And if it has units of volts RMS or amps RMS, it is obviously an RMS phasor domain. And the relationships that we are going to be developing over the next, pretty much the remainder of the class at this point, will all necessitate working in the RMS phasor domain. So you need to be ready to convert from the frequency domain to the RMS phasor domain if you ever see that your units aren't amps or volts RMS. Excuse me. All right, unless anybody has any questions, I think that's enough out of me. So on Thursday, we will cover complex power. I'll make sure to get all those notes and all that kind of good stuff uploaded like immediately after we leave. I'm also going to get the notes that I should have uploaded for today on as well. So in case anything that I did today didn't make a whole heck of a lot of sense, you'll have something to look back on and say, okay, maybe this is where that was coming from. All right, I think I also owe you guys a homework for today's stuff too, since I'm behind. So yeah, expect just a whole bunch of stuff to get thrown on Moodle within the next hour or so. I apologize for getting behind and forgetting to upload stuff. All right, is there any questions or comments or concerns or anything? Alrighty, I will catch you guys on Thursday. Have a good couple of days.